Our topic today is called the natural logarithm, and remember our goal was to try and determine the derivative of exponential functions. So last class we looked at the function e to the x and how we could get the derivative of that. Well, the other part that we're going to need to talk about a little bit is some logarithms and how that will apply if the base is e. So just a couple of reminders, because you've done logarithms already in advanced functions, but I wanted to make sure you remembered it. A logarithm is fundamentally just the inverse of an exponential function. It's a different way of writing it rather than having an exponent be an unknown. It's still an issue. There's lots of things that come up with logarithms, but because of exponent laws, that allows for some logarithm rules as well, and a lot of that makes things easier for us to solve, in particular exponential equations. So when I have that expression there, y equals a to the x, the same expression could be written in logarithmic form, which would be log base a of y is equal to x. Okay, so I don't know. Here's our example down below. Sometimes that's easier to picture. 1,000 is 10 to the 4. That's what exponential form looks like. Logarithmic form looks like this. The way you read that one is log base 10 of 10,000. Now do remember, if it's base 10, you don't have to put the 10 there. And most of what we do is in base 10, or at least it has been up till now. So that there would be equivalent. As I say, you don't have to show that 10 unless the base is something different. I'm going to put it back in for just a second though. The way you think of this is what it means. It says what exponent does 10 need in order to equal 10,000? And the answer to that question is 4. That's how I think my way through logarithms, because it's kind of a weird expression, right? This makes sense. 10 to the power 4 equals 10,000. That makes sense. You just evaluate it. To think through what this statement means, if you say it that way, what exponent does 10 need in order to equal 10,000? And the answer is 4. Okay, that works not too badly. So that's how logarithms work. The biggest reason we learned about them was to be able to solve some of these equations. 34 equals 5 to the power of x. And I'm going to slide this out. These were the logarithm rules, and these are ones that you would have learned in advanced functions. So I don't think there's anything here that's new for you. You would have seen all of these. The most important ones for us is this one here, I suppose. This is the one we're going to use to solve that expression. This guy we'll see once in a while. These are our couple of important rules. I'll show you one of those in a minute too. If you have the log of a product, you can write it as the log of one plus the log of the other. All of those can be proven using exponent laws basically, but I assume you did that already in the advanced functions course. Okay, sorry about that. So we're using those product and quotient rules. Hopefully they've been proven to you. The change of base formula is sometimes useful. I don't find I use it that often, but it is a nice little trick sometimes for some problems. Let me slide this out of the way. Make a mess of the screen. That looks really good. And we're going to try and solve this guy. 34 equals 5 to the x. So the way I would do it, I think this is the easiest way, is you just take the log of both sides. And that's log base 10, which is on your calculator, right? That's just your regular log button. But the advantage, the reason this works, is that rule that I said, when you have your exponent in a log, you're allowed to move that x down in front. So this is actually equivalent to this. And log of 34 and log of 5 are just numbers. So x is log 34 over log 5. And that's our exact value. And exact values are good. I will get a decimal here for you just so we can see it. 2.19 approximately. But that's a good answer right there too. Okay, that would be our exact form. 2.19 is kind of nice because you can actually picture it a little bit better. If you remember back to grade 11, we would have done that question using guess and check. And just as a little note, I don't think this is a big deal either because you would have seen it before, but other bases can be used, right? Base 10 has been our go-to base through advanced functions. But there's no reason why we can't pick other bases, and sometimes other ones are better. Um, if I have log base 4 of 64, and we're just trying to think about what that means. It means what exponent does 4 need in order to equal 64? And 4 squared is 16, but 4 cubed is 64. So if you have something like that, you can solve it that way too with a different base. Let's try some graphing. Graph the function y equals 10 to the x and its inverse, which is y equals log base 10 of x. So this is actually a tricky one to graph, not because, I should be careful there. It's not that it's that complicated, but it's really hard to get good points. So y equals 10 to the x. The y-intercept is 1. Right? Y-intercept is just 1. If I sub in x is 0, 10 to the 0 is 1. If I move over to x is 1, our next point is 10, right? 110. So we get that point. If I go to x is 2, the next point is 100. And we're not even close to fitting that, right? But we know that an exponential function has this property that it grows really, really quickly. So every time I move to the right, my y value is multiplying by 10. And then in the same way, if I move to the left, I'm dividing by 10 each time. So if x was -1, the y value is 0.1, which I can't even show very well in here. And then if I go to the next one, it's 1/100th, which is like impossible to show, right? And that's where our asymptote's kicking in. It's getting it closer and closer to the x-axis, but never actually get there. And I'll do my best. That's not very, well, that's not bad. For me, that's not bad. That would be our graph. That's y equals 10 to the x. Now to do an inverse, what we do is we just switch the x and the y coordinates. That's all that has to happen in order to get an inverse. So that point of 0, 1, change the order. 0, 1 becomes 1, 0. So it goes here. And then that other point, 110, we switch it, now it's 10, 1. The asymptote, which used to be along the negative x-axis, is now along the negative y-axis. It goes here, and here, and so on. It would look like that. And depending on what you remember from inverses in grade 11, the way an inverse worked was you ended up with a perfect reflection across the line y equals x. So the idea would be if I could somehow fold this screen in half along the dotted line, the blue curve and the red curve should superimpose right on top of each other. That's how an inverse is supposed to work. Okay, so this is what I wanted. I want to get into a base of e, which should work, right? And the next thing there, it says graph the inverse, y equals log base e of x. So instead of our normal base 10, we're going to use a base of e. And it should look similar, right? It's still an exponential function. Our y-intercept is still 1, because e to the 0 is 1. When I do e to the 1, that's just e, right? Which we said was about 2.718-ish. So around there. And if I try doing e to the power 2, I can fit that. E to the power 2 is 7.389. So around there. And I guess I'll put it in my calculator and see. E to the -1 is 0.367, but for all intents and purposes, as I'm graphing that, you can't tell where it is anyway, right? I know it's an asymptote on this side. Oh, that's not bad. So there's y equals e to the x, right there. Still an exponential function, a smaller base, and because it's a smaller base, it's not increasing as quickly, which has allowed us to see a couple more points on there. And I didn't do a very good job right there, did I? To get the inverse, all we're going to do is reflect the points. So 1, 0 is, or excuse me, 0, 1 is 1, 0. That second point there was 1 and 2.7, right? So now we're going to go 2.7 and 1, about there. And what did I say that other one was? 7 point something? So it's now 7 point something and 2. It's about there. And here's our asymptote again. And that's y equals log base e. Okay, so once you get your exponential function, you can get the logarithmic function just by doing the inverse, just by switching your x and y components. I should back up there before we get there. Y equals e to the x. What we said was ridiculously important for derivatives because the derivative of e to the x is e to the x. And if it's really important, then theoretically this should be really important too, using the base of e. And in fact, it's so important that they come up with another notation for it. So think of it like this. When I write log base nothing, if I don't put that number there, we said that's always a 10, right? That's always a 10. Well, what I'm trying to do now is I'm trying to write it with the base of e. But because of it, I mean, fundamentally math is a bit lazy, right? We're trying to shortcut everything if we can. So because this is so important, rather than writing log base e every time, we make up a new symbol, and it's ln. So it's ln, we pronounce it ln like L-A-W-N. So we say ln of x. And when we write ln, that is equivalent to saying log base e. Okay, so we don't write ln base e. As soon as I write ln down, that's assuming that we're using a base of e. Okay, but we're going to use that notation now instead of log base e. Shortens things up a little bit, and you'll see it on your calculator actually. Last class I asked you to find that e to the x button, and for me it was a second function. It's probably right on that same button, but as the normal function, just ln. It might not look like an L though. It might look like an I. Probably looks like that. So evaluate each of the following. Ln 59. All you do on your calculator is press the ln button and it should show up as ln. Press 59 and you're getting 4.077. What it means is e to the 4.077 would give you an answer of 59, right? What exponent does e need in order to equal 59? What about that? Actually, you could try doing that without your calculator if you just think that through. As I just said, this is saying what exponent does e need in order to equal 1? And equaling 1 is tricky, right? The only way you can do that is if the exponent is 0. But if you put in your calculator, it'll work too. Right? Ln of 1 is 0. Well, ln of e might actually be, it's a little bit tricky to put that in your calculator. To put that in your calculator, you have to do ln, and then do your e to the x button, and enter the exponent as 1. But the answer's 1, which makes a ton of sense actually, because it's saying what exponent does e need in order to equal e? Well, it's got to be 1, right? Last one here. And this is not a particularly exciting example, except that I wanted to show you something. If you think back to all of those properties that we had, log base log xy is equal to log x plus log y, right, was one of our rules. And that was for any base. We usually put a little a there. Well, ln is a log with base e. So all of those logarithmic rules still apply with ln because it's just a special case anyway. It's just a case where there's an e in it. So here, I've got ln 20 plus ln 5. That's going from here back to this form, right? So it's equal to 20 times 5. which would just be ln of 100, and then minus ln 25. And minus converts back to a division, right? So that's ln of 100 over 25. So just ln of 4. And you'd put that in your calculator and get 1.38. So okay, honestly here, you wouldn't save a whole lot of time. You could have done that in one step, right? I just wanted to remind you that all of these properties still apply using ln instead of log. Okay, all of the rules that we had before are still absolutely fine. Okay, we're going to try one little example, and I got one last little thing to ask you to do, but I like this example. It says the population of bacteria is given by P of t equals 200 e to the 0.094 t, and e is used fairly often actually in these cases. In grade 11, we started doing exponential equations like this, and we would usually put in something like a base of 2 there, 202 to the 0.94 t, and that would have given you a doubling rate. Well, it turns out e is actually a fairly good number to use in place of it. 2 is easy in grade 11 because you had no idea what e is. But it's called the natural logarithm because it actually comes up fairly often. It's a number that works relatively well for representing these sort of things. Anyway, what is the initial population? Well, to get that, we should sub in 0, right? So that means our exponent is 0. E to the 0 is 1, and 200 times 1 is just 200. So we get our initial population. And that's true for these type of functions. If you have a function of the form a b to the x, that number in front is always your initial value. When will the population reach 1,000? When will we get to 1,000? So this time we're subbing in 1,000 for p. Notice we haven't even done anything with derivatives yet, right? We're just talking about this. Whoops. Just talking about how to use these e's and lns. 200 e. Okay, so we're trying to solve for our exponent. The first thing I can do is divide both sides by 200. That'll make our life a little bit easier. And now we kind of have a choice. We've got an expression there where we're trying to solve for the exponent. So the way we would normally do that is we take the log of both sides, drop the exponent down. And whenever we did that, we did it a few minutes ago, right? We did log base 10, which is the easiest one to do because that's what's on our calculator. But in this case, since there's an e in the expression, using log isn't actually the best choice. Using ln is. And you'll see why really quick, actually. Remember, ln is still just a logarithm, so our rule will apply. We can take this exponent and drop it down in front. So we get ln 5 equals and the reason that it works so nicely is because of ln e. Usually, if we'd done log there, it would have been log base e, right? But ln of e is just 1. That was one of the ones we did a second ago. So that part disappears, and we get just this. So if we solve for t, we get that expression. Now that doesn't seem a whole lot better, but let me back up for a minute. How far do I need to go a ways? There. We solved an exponential equation here using log, and it was absolutely the right way to do it. But when we got to this part, our exact value had 2 logarithms in it, right? Log 34 over log 5. Well, that would have happened here. Oops. That would have happened here as well, except because we used ln, we were able to get rid of it. Ln of e was just the 1. So that's kind of nice. That turns out, by the way, to be about 17.12. But I don't want to use that. I'm actually going to focus on this. This is a really neat question, actually, to try and work with exact values for. So I'm going to use that t value as we get to part C. Part C says, what's the instantaneous rate of change when the population reaches 1,000? So the population reached 1,000 when t was ln 5 over 0.094. Okay, that's when it happened, at about 17.12 whatever was it. I can't remember what the units were now. Pardon me. So we want to find the instantaneous rate of change. Instantaneous rate of change means the derivative. So we need to find p prime of t. So let's remember p of t was 200 e 0.094 t. If I take the derivative of that, I can get the derivative of this because the base is still e, and we practiced that the other day. The constant in front stays. The derivative of e is just e, and we leave the exponent as it is. But this is a chain rule question. We have to multiply by the derivative of the inside, which is the 0.094. Now, if I simplify that just a bit, the 200 times 0.094 comes out to be 18.8. And remember, I haven't actually done any rounding yet, right? That 0.094 was exactly 0.094. So everything here is still perfectly accurate. I need to make this a little bit bigger again. What we were trying to find was when the population reaches 1,000, and we knew that happened when t was ln 5 over 0.094. So I want to find p prime. This looks a little bit ridiculous to write in, but it's correct. Ln 5, 0.094. That's the time. That's the time when we reach 1,000. So if I sub that into the derivative, right? 0.094. And then here we go, ln 5 over 0.094. Works out really nicely because that 0.094 on the top and bottom cancels. So we just get e to the ln 5. And e to the ln 5, you can put in your calculator. That was actually, it's actually one of our logarithm rules. If you have e to the ln anything, I'll put a k there, that's just equal to k. And you can try it, put in your calculator, you'll see that it works. 18.8 times 5. And 18.8 times 5 is exactly 94. So I really like that example because it started with a relatively ugly expression, 200 e to the 0.094. E is a irrational number, right? Goes on forever, no repetition at all. We solved that expression, and we had to use the natural logarithm, ln, in order to solve for t. We had to take the derivative, then we had to sub some logarithms back in, and in the end, the whole thing came out to be exactly 94. Exactly 94. There's no rounding there at all. So I kind of like that as far as exact values go, that you could actually carry through with it. If you hadn't, because remember we said it was about 17. Whoops. Oh dear. We said it was about 17.12. So you could have subbed that in and it would have worked okay too. But when you got your final answer, it wouldn't have come out as exactly 94. It would have come out pretty close. Okay, last thing for you to do, I just want you to try this to get ready for tomorrow, because we have another little lesson to do, which is trying to figure out how to take the derivative of an exponential function where the base isn't e, and this part will help. So just try evaluating those limits and then put ln 2 and ln 5 in your calculator and just see what happens. Okay, and that'll help a little bit with how we have to start next lesson.